Hello and welcome to the 9th session in the Measurement Error webinar series. I'm Sue Krebs-Smith from the U.S. National Cancer Institute, and I'll be moderating today's webinar. Before we get started, I'd like to point out the webinar is being recorded so we can make it available in our website. All phone lines have been muted and will remain that way throughout the webinar. Following the presentation, there will be a question and answer session, and we ask that you please use the chat feature to submit your questions. Another reminder, you can find the slides for today's presentation on the website that has been set up for series participants. The URL is available in the notes box at the top left of the screen. Other resources available include the glossary of key terms and notation and the recordings of the preceding webinars. Now I'd like to introduce our presenter for today, Dr. Raymond Carroll, Distinguished Professor of Statistics at Texas A&M University. He's a member of the faculties of Nutrition and of Toxicology and holds a courtesy appointment in the Department of Epidemiology and Biostatistics. He's been a principal investigator of a major NCI grant for the development of statistical methodology since 1990. Dr. Carroll's work on statistical methodology has found application in a broad variety of fields, including nutritional epidemiology. Dr. Carroll's topic for today is the estimation of usual intake distributions for multivariate dietary variables. Dr. Carroll.
Thanks, Sue. As everyone knows, this series is dedicated to the memory of Arthur Schatzkin, who I knew for 20 years from my various visits to NCI as a real visionary in the field. It's a real loss that he's not with us. And, of course, I want to acknowledge my collaborators. We've been working together. Larry Friedman and I wrote our first paper in nutritional epidemiology in 1991, and the whole group has been working closely together now for many years, and this webinar is a byproduct of that. So I'm a Texan, and I thought Texans are always proud of being Texans. So I thought I'd just say a little bit about where I'm from. I'm from Texas A&M University, which is in College Station, strategically located in between Austin and Houston, in other words, in the middle of nowhere. And I grew up in the northern central part of the state in a town called Wichita Falls. And those of you who haven't been to Texas may think it's totally flat, but there's three spectacular areas. One's the Big Bend National Park, which is just an unbelievable high desert with actually alpine at the highest areas. The Guadalupe Mountains National Park has 2,800-meter mountains, and it's also quite spectacular. And then there's the Palo Duro Canyon. It's the Grand Canyon of Texas. It's on the Red River of Texas, and this is a picture both of me and the Palo Duro Canyon, fabulous hiking place just south of Amarillo. And a lot of this work took place as part of the PhD dissertation of Seijun Zhang at Texas A&M, which appeared this year in the Annals of Applied Statistics. She's now working at Merck in the pharmaceutical industry. Okay, so the first thing we want to talk about is some background and some of our goals. But then we'll go on to the questions about what we're doing and our methodology and results. So the previous lectures have considered the relationship of dietary intakes and health effects, and they've talked about distributions of dietary intakes. In those cases and in this talk, when you're trying to understand the relationship of health effects and dietary variables, or when you're trying to do nutritional surveillance, it's typical that a 24-hour recall is available. In the health effects thing, it would only be available in a small sub-study, a calibration study. Future talks are going to discuss web-based instruments where it may become possible to use the 24-hour recall in large health effects studies. In the previous lectures, the number of dietary components have been reasonably small, and the difference between this lecture and the others is that, in my instance, the number will be reasonably large. It will be a multivariate problem, and our thinking has always been that the highly multivariate nature of diet analysis needs a new approach from what you've seen before. So here, part of our background is that the 24-hour recall is a good measure of intake on a single day, but it's not a very good measure of long-term intake because it doesn't account for day-to-day variability. The sample mean of the 24-hour recall values across a sample can be used as an estimate of the population mean, but it's not. The sample distribution of the 24-hour recalls is not a good estimate of the population distribution. And I'll repeat some slides that point this out again. All right, so the context here is there's going to eventually be other instruments that capture dietary intake on a single day, and nutritionists are going to want to understand longer-term average daily intake, not intake on one day, which we call usual intake, and we want to use this both in epidemiology and for nutritional surveillance. The data we're going to use is from the NHANES 2001 through 2004 survey of children aged 2 to 8 in the U.S. The data set that we're working with has about a little more than 2,600 children who have 24-hour recalls. 1,100 of them have 2 24-hour recalls. The other 1,500 only have 1 24-hour recall. It's a real survey, a real sample survey, and survey weights are incorporated into the analysis, but I'm not going to talk about them because they're technical details that are a little less interest. Okay. And the context we're dealing with is about dietary quality indices, which is an appealing way to summarize the multivariate nature of diet. And I'm going to define and discuss just one such index, the one we've been working with, the Healthy Eating Index 2005, or HEI 2005. And I'll try to be careful because there are other HEIs floating around, so I'll emphasize the 2005 HEI. The first goal here is to give realistic estimates of dietary intake distributions and dietary quality indices that account for the day-to-day variability. And then we also want to estimate the real relationship between nutrition and health outcomes while accounting for day-to-day variability in 24-hour recalls. So I'm going to focus mostly on the first problem, the surveillance problem, but we'll also do an analysis of the epidemiology problem at the end. So here are some questions that we want to address. Really, there's basically 2 questions. One is, what's the distribution of the usual dietary pattern scores, such as HEI 2005 or something like the Mediterranean Index? Now, the data I have is only for HEI 2005, but the methodology applies to other indices. And second, the relationship of usual dietary pattern scores and health outcomes is of interest. I should point out that there's a very exciting thing, because many of you know, going on in developing new tools for dietary assessments. The web-based ASA24 developed at NCI is one example, but it's not the only example. And it's exciting to think that in the future we're going to be able to get multiple 24-hour recalls or multiple other measures on individuals, and that will help us in all sorts of problems in nutrition. But large surveys such as NHANES will typically have at most 2 24-hour recalls. So it's even in the future we'll be still dealing with this problem. All right, so let me tell you about the HEI 2005. It's a composite score based on the USDA and HHS dietary guidelines for Americans. It's, as I said, one example of a multivariate dietary pattern score. I'm going to go through a bit to show you how multivariate it really is. And it has multi-components, in each of which are adjusted for energy. You've heard about energy adjustment previously. So all the components of diet that are measured in HEI 2005 will be adjusted for energy. And the final score, the total score, ranges from 0 to 100. And you want to be at 100, and you don't want to be at 0. I think I'm closer to 100 than 0, that's for sure. Here, this is a picture I got from the web of the USDA put out, and it lists some of the variables. You can see total fruit, whole fruit, total veggies, DOLs, I'll define all these, total grains, whole grains, etc. There are 12 components in the HEI plus the adjustment for energy. And there's a formula here, but I'll go talk about it in bigger font. I'm going to call DOLs dark green and orange vegetables and legumes. And the other thing that has an acronym is calories from solid fats, alcoholic beverages, and added sugars, which are the infamous SOFAs, which might be thought of as empty calories. And the Healthy Eating Index, in its 12 components, has various maximum scores. So the fruits, the grains, the DOLs, and the total vegetables get a maximum score of 5. Milk, meat and beans, oils, saturated fat, and sodium get a maximum score of 10. And SOFAs, you can get a maximum score of 20. And so the total, if you get a maximum score on everything, you get 100. And the formulas look sort of like this. So total fruit is one of the components, and what we do is we adjust total fruit by kilocalories. So that's the adjusted total fruit, and then the score increases linearly up to 0.8 equivalents per 1,000 calories, or 1 kilocalorie, and with a maximum score of 5. And it's not linear because what happens is it's nice and linear up to 0.8 cup equivalents. But then after that, it's flat. The score stays at 5. So it has a little a change point as it goes along. And all the components are like this in the HEI. For saturated fat, energy intake is the percentage of energy from saturated fat. And it has a fairly complicated score, a way of measuring things. If you're below 7% of your calories coming from saturated fat, you get the maximum score. If you're above 15%, you get 0. And in between there's these formulas which are sort of hard to sort out without a graph. But that's how they all work. All these components have this little bit of nonlinearity in them. This is the empty calories. If your percentage of energy from SOFAs is more than 50%, you get a score of 0. If it's less than 20%, you get a score of 20, and it's linearly interpolated otherwise. So, and I could go through on all the other 9 ones, but I hope you get the idea of what it's like. And now what I want to do is talk about long-term HEI total score. I don't want to talk about short-term HEI total scores based on a single 24-hour recall. So the long-term adjusted whole fruit is going to be the long-term daily average number of cups of whole fruit consumed divided by the long-term daily average of kilocalories. And these are going to be my usual intakes, which will lead to the long-term HEI total score. So that's the HEI total score. Here's some results from that HEI total score. I thought instead of introducing the methods first and giving the results, I thought I'd give the results first and then the methods. This is the actual result in children aged 2 to 8 in the United States for the total score. And in red is the total score, the distribution of the total score. This is a histogram. These are smooth histograms. It's the distribution. The red is that of the single 24-hour recall, and the blue is our method, which adjusts for the day-to-day variability in 24-hour recalls. And you can see that what happens with a single 24-hour recall is that you're overestimating the percentage of diet scores less than 30, and you're also overestimating the percentage of diet scores which are greater than 80. So there's biases in both directions. Here's a picture of a not a very good plot, really. This is, if I'm looking for the 50th percentile, I will try to do this. Let's see, there we are. I'll put it right here. That's the 50th percentile. I just go up and then read off. So the median is about, for the 24-hour recall, is about 50, and the median for our method in blue is also a little bit more than 50. But I think the crucial thing to see in this graph is that we estimate that that 8%, which is still a pretty large number, but 8% of children have a total score, HEI 2005 total score of less than 40, whereas the single 24-hour recall says 25% have a total score of less than 40. So it's quite a big discrepancy. And the other thing happens on the other end in high scores. And this is now just our estimate of the total distribution of the total scores, the histogram of the total scores. And essentially no children in the U.S., we estimate, have a total HEI score, HEI 2005 score of greater than 80. And that's sort of interesting because about a year and a half ago, the White House Task Force on Obesity was considering a goal that all children would have an HEI 2005 usual intake total score of greater than 80, and we estimate that the 99th percentile is actually less than 80. It's 79.4 is our estimate. So when they heard about our results and got other information, the task force changed its goal to have children move to a mean of 80. Go back. So that's still ambitious because we estimate that the mean is 53, a little bit more than 53. So to meet this goal is ambitious and hopefully can be done in the near future. Okay, so those are the results. The basic point of the results is that using a single 24-hour recall can result in some very large biases when you're looking at the distributions of intakes and HEI total scores. Our assumption that we've made is that 24-hour recalls are unbiased measures of usual intake on a given day, and it fixes the discussion, makes it statistically feasible, and it also basically states that 24 hours pretty accurately reflect a single day's intake. But what we want to do is take into account the day-to-day variability. And I'm going to repeat a few slides that you've seen previously in at least Janet Tuz's talk, but they're still important and they're still useful to remember what's going on here. So the first thing is that nutrient data don't look like this. There's a large literature on measurement error and measurement error modeling and corrections, and they're often based on the idea that the data are beautifully bell-shaped. In particular, such as the nutrient intake data. And that's not the case in general, but this is the beautiful picture where in green is the usual intake, in red is a single day's intake. And the point of this picture is that while the two methods have the same mean, the 24-hour recall, single day's 24-hour recall is much more variable than usual intake. This is a picture you've seen from the Eating at America's Table study for folate intake. Green, again, is usual intake. Red is a single day's intake. And you'll notice, once again, that the single day's intake it's shifted to the left, so it's much more right-skewed than usual intake. It has more values that are low, and it has more values that are high, just as we've seen in the HEI 2005 total scores. And so to deal with the skewness, we try and go back to that beautiful picture I had, the nice bell-shaped curve. Everybody loves bell-shaped curves, Gaussian-like distributions. And so what we do, and it's typical to do this, is we transform the scale of the nutrient, do a measurement error correction, and then back transform to the original nutrient scale. So this is an illustration. You've seen this before, but this is what we do. We look at that folate intake distribution. We say, oh my goodness, that's ugly and skewed. We then transform it so it looks like it's bell-shaped, but that's a single day's intake, so it's too variable. We then do a measurement error analysis in this transform scale, get still a bell-shaped curve, but a lower variability, and then we back transform to the original scale. So we're talking about distributions of folate intake, not distributions of transformed folate intakes. And we're going to do this on all 12 of the components of the HEI 2005. the thing that makes HEI 2005 challenging is that it has episodically consumed components, and it has lots of them. So in this picture you can see here, this is the percentage of 24-hour recalls in the NHANES study for children where they report no intake of these 6 quantities. So 40% of the 24-hour recalls in the data set report no intake of whole fruit, 42% no intake of whole grains, and 50% no intake of DOLs. And total fruit, milk, and total veggies are lower. But this is a very challenging problem. It's a really hard problem because there's 6 of these things, and in general there can be even more that are episodically consumed. So what you get, another picture that you've seen, this is a whole grains picture for men from EATS. What you get is a spike at 0, where there's reported no whole grain intake, and then on consumption days, a very right skew distribution. So it's it's the combination of the blue and the red that makes this a fun statistical problem. We want to take into account the fact that these zeros are overrepresented for usual intake. And for a single food, we developed a flexible modeling framework, which is we call the NCI method. Even though I'm at Texas A&M and was a collaborator on this, most of the work was done at NCI, and this is a reasonable thing to call it. It's based on the SAS program called NL Mix, Nonlinear Mixed Models, and you can, as you know, you can get it from the web. So in the HEI 2005 analysis, what we're doing really is trying to go from a single episodically consumed dietary component, which the NCI method can handle, to multiple dietary components, which the NCI method cannot handle. It's important to understand that we actually need a multivariate model. I can run the NCI method on every dietary component in the HEI 2005 separately. It works great, and we've done this. And that allows you to estimate the mean of the HEI total score in a population. But by running it separately and then adding up things, it doesn't get you the distribution of the total scores. The only thing you can get by running the NCI method 12 plus times is the mean and not the percentiles. And so the percentiles need the multivariate model. And I just think it's a really cool problem for a statistician to work on, and it's a really cool problem because the HEI 2005 is an interesting way of measuring dietary consumption. So we have to do other things now. That's the bottom line. There's no current way to analyze the HEI 2005 to do distributions of usual total scores. The PROC NL Mixed cannot do these things. It's technically infeasible for them to use it, and so we need a new approach. I'll talk a little more about why it's technically infeasible. So what we have to do is figure out a model that allows analysis of HEI 2005 total score, and we have to figure out how to compute those things. I'm going to spend a little bit of time on the model, less time on the computation, which is highly technical. So this is, we use the same notation from other talks. I is going to be a person, and J is going to be a replicate of the 24-hour recall. K is going to be an index depending on which dietary component you've got. There's 6 episodically consumed dietary components, 6 daily consumed, plus there's energy. So K could, in principle, run to be a pretty big number. And what I'm going to do instead of, because we'd need a 90-inch screen to do the whole thing, I'm just going to do 2 foods and energy and show you what the model looks like. So what we have to do is formulate consumption to allow day-to-day energy to be correlated with day-to-day consumption. But we need to know what do we mean by consumption? What do we mean by a distribution on consumption days? So first of all, I'm going to say generically that X is going to denote covariates, demographics, or the food frequency questionnaire if it's available. And I'm going to make little u be the person-specific biases. These are a really crucial concept that you've seen before, namely that even if I and another person share the same demographics, we're going to have different long-term intakes because we're different. And so this acknowledges that people their dietary intakes can't be just described by demographics. And then finally, epsilons are going to be the day-to-day variability that floats around in here. So there's three components. The first thing is consumption. Well, consumption is a funny concept, but we use a technique that comes from econometrics, and that's called choice-based sampling. And what it says is, well, there's this latent variable. I have the X beta here. That's the demographics, the effect of demographics. The U is the effect of individual persons, and the epsilon is the effect of day-to-day variability. And I will never see this W, but I'm going to say that consumption of the food is equivalent to this latent variable, this unseen variable, being positive. And this is a really good way to model consumption. And when the food is consumed, it's positive. We've seen it's badly skewed. And so we're going to transform the data. We use the Box-Cox transformation, which is the logs, the square roots, the cube roots, etc., which really are very effective methods to transform data to normality. Then after we transform the data, we're going to say that on consumption days, the transformed data also follow the same kind of model. There's the effect of the demographics, the effect of individual people, and the effect of day-to-day variability. Sometimes this W is observed on a consumption day. It's observed, but it's not observed on a non-consumption day. So it's latent on a non-consumption day, but we get to see it on a consumption day. And then finally, well, we'll get to finally a little early here, and I'm going to denote a covariance matrix with the symbol sigma. We have to have at least one Greek symbol in here other than a beta, and the sigma denotes the variances and the correlations of each of the variables. And finally now, I'm going to add in energy. Our latent variable, turns out, in HEI 2005 has 19 components. So it's a 19-dimensional covariance matrix. There are two components, two variables for episodically consumed components, one for daily consumed components, and one for energy. So we have a pretty large dimensional covariance matrix. And energy, of course, is transformed. It's skewed, and we transform it in the same way with demographics, individual effects, and day-to-day variability. And our model proposes that on the transform scale, the individual effects are normally distributed, and on the transform scale, the day-to-day variability is normally distributed. And our big model is just a generalization of this to add all 13 components of the HEI 2005. So having defined a model, and it's a 19 dimensions is a lot of dimensions to work with, but it's feasible to do this, and we've got some nice results. I want to show you a little bit about computational issues and discuss them. There's a lot of technical issues related to fitting this model for HEI 2005, and I'm a technical statistician, and so I found it extremely interesting to work with, and Sejin Zhang got a PhD out of it, but it really would be boring for you, just mind-numbing. In fact, the details of the computations take 8 published pages in the Annals of Applied Statistics, and I guess I could amuse my friends by showing them, but I won't show them to you. But what it is, in the framework of statistics, it's an example of a high-dimensional, highly nonlinear, mixed effects model with excess zeros caused by the episodic consumption of the 6 dietary components. It ends up with 19 components in the model, and SAS-NL mixed, which is a very good program if there's only 1 or 2 dietary components, simply will not run. We've tried it, and it doesn't run. It just doesn't give answers. And I don't think it's a matter of having a big enough computer. It's a matter of just the problem is too large. So it just doesn't run. And the computational issue is that the day-to-day variabilities are correlated. So my consumption of calories and my consumption of sofas are going to be correlated. If I have a lot of sofas, I'm going to have a lot of calories, most likely. And it's also true that how individuals differ from one another, those components they use are also going to be correlated. Because if I tend to want to have whole fruits, I'm likely to tend to want to have non-whole fruits. And the standard statistical technique called maximum likelihood requires integration, areas under the curve of a function, but we've got 19 dimensions. And doing 19 dimensions, it's hard enough doing one-dimensional integration, but doing 19-dimensional integration is, in this context, not really feasible. And while I love my model, I love our model, it's worked really hard to make it computationally feasible with parameters that are free to roam about as little happy people, or they're on a fixed interval. Standard software doesn't work. So what did we do? Well, there's been a revolution in statistics and statistical computing in the last 20 years using Monte Carlo techniques. Statisticians, computer scientists, bioinformaticians, they're all moving to Monte Carlo techniques for computation of integrals. There's an enormous literature now on how to do this, and I can't resist advertising a book that my genius colleague Feng Liang wrote with myself and Chunhai Liu, who's at Purdue. So there's a lot. We know a lot about Monte Carlo computation. We know how to use Monte Carlo to do integration. And the most commonly used method is something called Markov chain Monte Carlo. I've resisted the temptation to say MCMC, which is the term in statistics that people use. And those of you who are statisticians or know a friendly statistician that may have heard of Gibbs sampling and Metropolis Hastings steps. We were able to use Markov chain Monte Carlo to do the integration. Mostly the steps were very easy, but we had to write our own program to do the computation. So there's no standard software that can be used in this particular problem. Because we were doing a survey sample, we used balanced repeated replication from the survey sample literature to get standard errors, and we used Markov chain Monte Carlo to get the estimates of all the parameters. You have to be careful. So in this, if you consume whole fruit, you consume total fruit. So we separated them out and treated them as 2 different dietary components. We did the same thing for whole grains and total grains, and we did the same thing for total veggies and DOLs. Small point. And then after that, we get total fruit by adding together whole fruit and fruit juices. So we've got the parameters estimated. We fit our model. It describes the usual intake of these, usual energy-adjusted intake of these 12 dietary components in the HEI, and we're able to then use more Monte Carlo to get the distributions of the total scores and the distributions of the joint distributions of each of the component scores. And I know this is a really ugly thing to write down, but what I've got in what the HEI 2004 score really consists of, it's a very complicated function, T, which involves all sorts of cool things, of covariates, parameters in the regression associated with the covariates, the individual, how people differ from one another, their covariance matrix, the covariance matrix of day-to-day variability, and the person's actual person-specific bias, which we can't see. We can't actually observe that, but we can use the computer to generate these person-specific biases. And then what we do is we make up, it's a statistically allowable thing to do. This gives us, we put in these things we've generated by computer, and then we get the empirical distribution with survey-weighted empirical distribution of these generated total scores, and that's how we get the distributions that you've seen in our previous slides. It's a very complicated method. It is a complicated method. It's very easy to program, but it looks like a complicated method. But we're very concerned about whether we programmed it correctly. Sajan and I wrote our own separate codes. Dennis Buckman, who works with IMS, wrote his code. And then we got the same answers, and we also verified this by looking at the NCI model, the NCI method, and we took each component score separately, one at a time, and our answers are in very close agreement with these results. So we're really confident about our numbers, and of course, you have to do a multivariate model if you're interested in the distribution of the total score. Okay. And then finally, I want to give a few brief results about epidemiology. We've applied the model to the analysis of the NIH AARP Diet and Health Study. And our outcome was colorectal cancer. And we've done this analysis separately for men and women. And what we want to do is study the association of dietary patterns using dietary quality indices such as HEI 2005, adjusted for measurement error and day-to-day variability, and the health outcome, namely colorectal cancer. So this is our goal. We want to get but the key point is we want to get the dietary quality indices effect after adjusting for measurement error. So we did a survival analysis using person years, and there were a number of variables in the model: age, categories, ethnicity, education, BMI, smoking status, energy and hormone replacement therapy for women. There wasn't any physical activity energy in the model. And the HEI total score was also in the model, as was energy, as I said before. We fit this as a log linear continuous risk model. And because it's a continuous risk model, we're able to use regression calibration. So the analysis was done first for using the food frequency questionnaire and computing the HEI 2005 total score and energy using the food frequency questionnaire. And then the second analysis was our measurement error corrected approach based on our big model and using regression calibration. And the same covariates were used to fit the HEI 2000 total score in the calibration study. So the only 24-hour recalls we have are in a calibration study of about 900 people for each gender. We use Monte Carlo, that's a theme here, to do the regression calibration and for both energy and the total score. And we use bootstrapping to estimate standard errors in the regression calibration analysis. So the results are going to be pretty much what we expect. What we've seen before is that one of the effects of measurement error is typically to get relative risks or baseline hazards which are closer to 1 than a measurement error corrected analysis. That is, the effect of using an error-prone instrument is to lead to a diluted effect in appearance, and that is and underestimate the relative risks associated with a bad diet. So here we've got a pretty big model. We have 2 error-prone components, the total score and energy. We've got 37 other covariates for men, 38 for women. And so this is a pretty complicated problem where it's hard to actually tell you exactly what's going to happen, so we had to actually do the calculations and not do the theory here. And here's what we get. If you use the FFQ, the relative risk from going from the 10th to the 90th percentile for women is estimated as 0.8. And after measurement error correction, this is based on the total score, we get an analysis that says the relative risk is 0.62. So this is what we expect in measurement error, that the impact of measurement error is to dilute the effect, sending it closer to the null value of 1. And this is a pretty good attenuation here due to the measurement error and biases in the food frequency questionnaire. The p-values also change, and this is a unusual thing that happens because of the large dimensionality of the problem. The 95% confidence interval for the relative risk ignoring measurement error for women is from 0.68 to 0.98 with a p-value of 0.04. For our usual intake analysis, the confidence interval is longer, but it's shifted way down, and its p-value is even smaller, 0.02. That's not what you typically see, that the p-value goes down, but it does happen, especially here in this highly multivariate context. So again, we have attenuation, and in this context, we actually have the effect of measurement error is to raise the p-value almost to the null level. So I'm going to summarize here what we've done. 24-hour recalls have large amounts of day-to-day variability. And our problem was a problem of adjusting for this day-to-day variability to try and get usual intakes when we had multiple episodically consumed foods and multiple nutrients. And that's a problem that's been unsolved, and it's extremely challenging. But we were able to provide what is right now the first solution to the problem, and we're applying these to other quality indices as we're speaking. The method that we developed allows us to understand dietary patterns, estimate distributions, consider risk models, etc. And we're very happy with that. The original programs that I wrote and that Sejin Zhang wrote were written in MATLAB, which is not particularly user-friendly language. It's good for scientific computing, but not for field use. And so the NCI is developing a SAS version of our model that will be a generalization of the NCI method in these more complicated problems. So thanks very much for your attention, and I guess Sue will now take over.
Well, I'll take over for a bit. Thank you very much, Dr. Carroll. And we are going to move into the question and answer period of the webinar now, and we have a couple of questions to get started. One thing that you mentioned was that the assumption that 24-hour recalls are accurate measures of dietary intake and that they're unbiased. But although that's an assumption, we know that that's not really true. So given that there are some systematic biases, do we know how the results would be affected with this bias?
Well, we don't really, the trouble is we don't really know what the biases are. So for anything in this, say in the HEI 2005, other than energy, where there's doubly labeled water to understand the bias, we found in dealing with protein and with energy that the effect of bias it's there, but it's modest compared to the effect of the day-to-day variability, which is really quite large.
Okay. When you were talking about episodically consumed foods, you mentioned the HEI 2005. You said had 6 components that were episodically consumed. One of those was total veggies, with 3% that didn't report any consumption of total veggies. How do you determine episodic foods? 3% sounds like a low number for determining episodic.
It is a low number. Well, how I did it was I referred to my friendly nutritionist who suggested what to do. But I also redid the analysis by substituting in for those 3% people the 1/2 of the minimum amount of vegetable consumption across the consumption days, and the analysis doesn't change very much. The only case the thing you don't want to do is go really down to an extreme. I think anything below 3% is probably a bad idea to treat as episodically consumed. If it's like 0.5%, any statistical method is, especially with these 24-hour recalls, is going to have a hard time estimating the consumption part of the model, the probability of consumption, because the probability of consumption would be so high.
Okay, while we're talking about the individual components of the HEI, here's another question related to that. This person asked, fruit seems like an aggregate of the consumption of different fruits, apples, oranges, and so on. Do you think it's better to apply this method before or after aggregating to get total fruit consumption?
Oh, it would be better to aggregate. I mean, from a computational point of view and a numerical stability point of view, it's better to aggregate, because if you were to run this analysis on apples separately and bananas or whatever separately, you start to raise the dimensionality of the problem very, very, very rapidly, and I think that it's going to be really hard at some point to get very reliable answers. It's possible to run the model, but unless you're really interested in the different components for HEI analysis, it's certainly better to aggregate.
Okay, I'm glad to hear that. I think it would get very complex. You have talked about the analysis with HEI 2005, but you also mentioned that this technique that you have would be workable for other dietary scores, such as the Mediterranean dietary score. Have you applied your method to the Mediterranean dietary score, and what would be the results from that, if so?
No, I haven't applied it to the Mediterranean diet score. The part of the NCI's programming is to build a methodology that will enable any sort of dietary pattern score to be done. So our current programs were geared to various HEI measures and on a one-off kind of thing, and that we know how to do it completely generally, and this is why we have a professional programmer working on putting together a SAS program.
Okay. One characteristic of the HEI 2005, it adjusts all of the individual components for energy intake, but of course absolute energy intake is not figured into the score. Can you comment on this a bit?
Well, that question has been raised as I've given talks, and from the perspective of, for example, risk measurement, we do include energy in the analysis, but the total score is defined, and the HEI 2005 total score was defined, and we went with the definitions to try and understand the statistical properties of that particular measure. But it isn't a problem to work with different measures that don't deal always with energy-adjusted dietary components.
Okay. From a nutritional point of view, I'll just add to that that the HEI 2005, without including absolute energy intake, it then reflects really the quality of the mix of foods, and you can look at any set of foods, and because you've got this density-based standard. So we found that a useful feature of the HEI 2005 for those reasons. On another theme, there was some question about the distributions of scores. It says the distribution of total scores are remarkably normally distributed. Would you expect that?
No, this was just with the kids, and that's just what happens with that data. We've worked with the NHANES for men over the age of 20, and they're actually quite less skew. They're not even right skew, they're less skew, and very, very noticeably less skew. So it's going to depend on the population as to whether things are normal, right skew, or left skew.
Okay. Why do you think the 24 hours recalls are shifted to the left?
Well, it's because there are lots of zeros in them, and so what happens is if you apply most of the dietary components that are episodic, more is better. More results in a higher score, and because the scores are highly nonlinear, whenever you get a zero, you get a zero in their score, and so it just moves the thing over.
Okay. It seems your analysis doesn't include the possibility of never consumers. There may be some components where people, for some individuals, that they truly do not consume the component at all. What would happen if you needed to include that possibility in the model?
Yeah, in this program, we don't think that has. We've done some analyses and don't think that for the HEI 2005 that's going to be much of an issue. But we are working on, I have a postdoc and a graduate student working with me and with people at NCI on developing methods to handle episodically consumed foods with never consumers in this complicated context. And we're programming as we speak.
Okay. Now we have several questions that are related to the model itself. One thing, when you were describing the different terms that you would use in the model, you said that K would denote an index. Can you describe what you meant by an index? Because it didn't seem like you meant the index, the HEI index, but some.
No, that's right. I'm sorry. Yeah. K describes. So, for example, if I have, let's say, whole fruits, I've got two things going on with whole fruits. One is whether they're consumed or not, and secondly, I've got going on what is consumed on consumption days. So I set K equal to 1 for whether there's consumption and K equal to 2 for amounts on consumption days. And then I would do this for each of the 6 components. So I'd have another K, so 3 for, say, fruit juices consumption and 4 for the amount of fruit juices on consumption days. And I work that up. So it's really not a very good, index is probably the wrong phrase.
But when you were talking about those 19 dimensions, those were 19 Ks in your
Yeah, 19 Ks, yes, indeed.
Okay. All right. The proc-NL mixed, can you talk a little bit more about the issue of integration being too great and why that's such an issue, why that wouldn't work?
Yeah, so what happens is that proc-NL mixed uses a method called maximum likelihood, and so it tries to integrate out, in other words, to get rid of those U's, the person-specific biases, because they're not observed. And so maximum likelihood can only work on things that are actually observable. And so it tries to integrate out these person-specific biases, the 19-dimensional U's, and that simply NL mix can't handle, just physically can't handle that high a dimension. So any of these high dimensional problems that involve latent variables such as the person-specific effects are going to have to go with some version of Monte Carlo computation. When you get past about dimension 3, there's really no place else to go but Monte Carlo.
Okay. Now, that relates to this next question that has to do with the runtime for the computations, and how long does it take to run the model for the total HEI score distribution. And I wonder if you could talk about that in relation to the models that you developed for this, and then compare that maybe to what it's like to run a single food with the NCI method.
Right. Well, the single food adjusted for energy, the NL mixed, so if I just look at that problem alone, we have a paper where we showed that the single food, this is not the NCI method, although it's a generalization of it. The Monte Carlo computation is much, much faster. It's on the order of 3 minutes in MATLAB on a good machine. For the HEI, it's a couple of hours for all components to run. I'm very, very conservative about these things because I don't mind 7 hours or 3 hours or 4 hours if I'm going to put some numbers in a paper. There are ways of cutting it down to about 25 minutes, but I prefer to, in the Monte Carlo computation, you have to do do a lot of repetitive things, and I like to do lots and lots of repetitive things to guarantee the stability of the final answers. But we have no trouble doing bootstrapping or balanced repeated replication on these sorts of sample sizes. It's not very long.
Okay. And do you expect that the timing would be similar with the SAS programs that NCI is developing?
Yeah, it should be pretty similar. That's right. I haven't taken into account any of the really fancy features of MATLAB for parallel computing and things. I've tried to keep it very vanilla so that the SAS program timings would be roughly the same. And some of the initial analyses that Dennis Buckman has done suggest that the timings are going to be about the same.
Okay.
And the method's very, very numerically stable, which is not true with NL mixed with episodically consumed food plus energies. They sometimes has lots of problems with instability.
Okay. Also related to the model and your methods, there's a question. You use MCMC, which is usually used in Bayesian statistics. Are you doing a Bayesian analysis?
No, I'm not doing a Bayesian analysis. Bayesian analyses are, especially in surveys, are almost impossible. I find it's a very controversial field how to make confidence intervals being Bayesian in sample surveys. The Markov chain Monte Carlo, which is used in Bayesian statistics, is also a perfectly acceptable statistical method for non-Bayesians. There's a large theory that says it's effectively, if you could compute those integrals and do maximum likelihood, then you would get the same answers using these MCMC things. So it's just a way of getting a maximum likelihood estimator that's actually feasible to compute.
Okay. In the example that you gave from the N. Haynes analysis, you had mentioned that there were a certain number of children with a single 24-hour recall and another set with two 24-hour recalls. Did you include the children that had only one recall in your analysis?
Oh yes, for sure. For sure. It makes they contain valuable information and actually lower the standard errors by about 25%, which is non-trivial. For sure, we used all the data.
Okay.
More 24-hour recalls are good, but having one on 1,500 people. Remember, 24-hour recalls are, by assumption, unbiased for the mean. So, if nothing else, they can be used to really increase the precision of your estimate of the mean.
Mm-hmm. Never throw away information, right?
Never throw away information. Yeah.
Okay. All right. Well, that brings us to the end of our questions. Thank you very much, and thanks to our audience for joining today's webinar. Please do join us next week for Webinar 10, when Douglas Methuen will discuss combining instruments as a strategy to reduce the effects of measurement error. That ends today's webinar. Thank you.